Hello future engineers, welcome to my YouTube channel. If you're still new to my channel and you like what I'm doing, please don't forget to share my videos to your friends and to your friends' friends. Also, if you find my videos interesting and important to your studies, please don't forget to subscribe. Uh, that's the one way. That's one way you can help me promote my channel to keep me going, inspired and refreshed. Problem 32. A concrete dam retaining water is shown in the figure below. The specific weight of concrete is 23.5 kilonewtons per cubic meter. Compute the factor of safety against sliding, overturning, and the pressure intensity on the base. Consider two cases. Letter A, the foundation soil is impermeable, and letter B, the hydrostatic uplift varies uniformly from full static head at the heel of the dam to zero at the toe, and that the coefficient of friction between the dam and foundation soil is 0.45. So here is the cross-section of the dam, and let's assume 1 meter width perpendicular to the screen or to the board. So for the solution, let's have uh, bound boundary for this water uh, enclosed by the vertical line through this end, which is the hill, and the water surface as well as the face of the dam. And let's call that length x1. And we have the horizontal force projected on this face, and since the pressure distribution is triangular, it is located 1/3 of 15 from the bottom, so 5 meters from the bottom. And we have x1 by similar triangles, x1 as to 15 equals 3 meters as to 18. So solving for x1, x1 is 2.5 meters. So therefore for f1 it is gamma barred H area, gamma of water 9.81, barred H is half of 15. The area is rectangular, 1 meter wide by 15, so 1 by 15. So F1 is equal to 1,103.625 kilonewtons. Another way of computing M1, draw the pressure diagram, and it is equal to the volume of the pressure diagram. It will give us the same answer. Then for W1, this distance is 1/3 of x1 or 2.5 over 3, so that's 5 over 6 meters. Then we have weight 2. This distance is 1/3 of 3, so 1 meter, as shown. Then we have weight 3, masonry, concrete masonry. This distance is 1/2 of 5, so 2.5 meters. Then weight 4, which is concrete masonry, and this distance is 1/3 of 3, so 1 meter. So weight 1 is volume of this, or weight of this water here, and it is specific weight of water times volume of water, 1 meter to the board. And this is the toe, and this is the heel. So weight 1 is equal to 9.81, 1/2 of 2.5 times 15 times 1, so 183.938 kilonewtons. Weight 2, this is concrete masonry, so 23.5 times volume, 1/2 of 3 times 18 times 1, so it is 634.5 kilonewtons. Weight 3 is weight of this concrete masonry, 23.5 times 5 times 18 times 1, so it is 2,115 kilonewtons. Weight 4 is identical with weight 2, so weight 4 equals weight 2 equals 634.5 kilonewtons. So for part A, there's no uplift pressure. The foundation soil is impermeable, So therefore, Ry is the sum of the weights. So this is Rx and we have Ry. Rx is simply F1, summation versus horizontal, and Ry is sum of the weights. So this distance of Ry from the toe is denoted by bard x, and we have Ry summation of weights, weight 1 plus weight 2 plus weight 3 plus weight 4. So Ry is equal to 3567.938 kilonewtons upward. Rx is just F1, and therefore it is 1103.625 kilonewtons. Then we can now compute factor of safety against sliding, which is coefficient of friction Ry over Rx. So coefficient of friction Ry over Rx. So F factor of safety against sliding is equal to 0.45 times 3567.938 divided by 1103.625. So factor of safety against sliding is equal to 1.455. Factor of safety against overturning is righting moment over overturning moment, where righting moment is moments due to the weights. So in this figure, these are clockwise moments. So righting moment equals weight 1, 183.938 times quantity 11 minus 5 over 6. 11 is the width of the base of the dam, which is 11, 3 plus 5 plus 3, capital B. Then minus 5 over 6 plus weight sub 2 times 3 plus 5, 8 plus 1, 9. So plus 634.5 times 9 plus weight 3, 2115 times 3 plus 2.5, 5.5. So plus 2115 times 5.5, then plus weight 4, 64.5 times 2. 3 minus 1 is 2, so times 2. So righting moment is equal to 20,482 kilonewton meter. Then for overturning moment, that's due to F1 and uplift supposedly, but there's no hydrostatic uplift, so it is just due to F1. So F1 times 5. So overturning moment 1103.625 times 5. So overturning moment is equal to 5518.125 kilonewton meter. So we can now compute factor of safety against overturning. It is equal to 20,482 divided by 5,518.125. So factor of safety against overturning is equal to 3.712. Then let's solve for bard x. Summation moment about the toe equals 0. Ry times bard x, that's overturning moment, equals righting moment minus overturning moment. So Ry times bard x, that's overturning moment, plus F1 times 5, that's overturning moment, equals moment due to the weights righting moment. Therefore, bard x is righting moment minus overturning moment divided by Ry. So bard x is equal to righting moment minus overturning moment over Ry. Substitute bard x 20,482 minus 5518.125 divided by 3567.938. So bard x is equal to 4.194 meters. And this is compared to b over 3. So b over 3 is 11 over 3. So 11 over 3 is less than bard x, and bard x is less than b over 2 or 11 over 2, which is 5.5 on the next slide. So b over 3 is, which is 11 over 3, is less than equal to bard x prime, which is equal to 4.194 meters, and 4.194 meters is less than b over 2, which is 11 over 2 or 5.5. So this means that Ry, or the reaction at the base, crosses the base within the extremities of the middle third. So this dam is designed in a good manner. So E is 11 over 2 minus VARD X, 4.194, so 1.306 meters. So that we can see this on the picture. Let's have the cross-section of the dam. So this is the center line, and the distance between the center line and Ry is the E, as shown in the figure. That's E. So we can use the combined stress formula. Combined pressure formula, Q equals Ry over B quantity 1 plus 6E over B. So we use plus for the soil pressure at the toe because Ry is closer to the toe, and minus for the soil pressure at the heel because the heel is far from Ry. So Q is Ry over B quantity 1 plus minus 6E over B. Everything is known, Ry, B, and E. So Q is Ry 3567.98 over B11 quantity 1 plus minus 6 times 1.306 over 11. So again, use plus for Q, soil pressure at the toe, and minus here for the soil pressure at the heel. So Q at the toe is 555.4 kilopascals, and Q at soil pressure at the heel is only 93.30 kilopascals. So that's for part 1. For part 2, hydrostatic uplift is present, and it is full static head at the heel, 0 at the toe. So the soil hydrostatic pressure diagram would look as shown. So this is 9.81 times 15 here. So 9.81 times 15, and it is 147.15 kilopascals. Then this is the uplift force, which is equal to the volume of this uplift pressure diagram. And this is 2/3 of 11, so 22 over 3 from the toe. So uplift is 1/2 of 11 times 147.15 kilopascals times 1. So it is 809.325 kilonewtons. Because of this, Ry will be affected. The new Ry is Ry previous, which is 3567.938 minus uplift pressure. So Ry prime equals previous Ry 3567.938 minus uplift 809.325. So Ry prime is 2758.613 kilonewtons. Also, uplift will have overturning moment about the toe. So the new value of overturning moment would be previous overturning moment, then plus moment due to uplift, which is uplift force times 22 over 3. The righting moment is unaffected. So overturning moment prime is equal to previous overturning moment 5518.125 plus the contribution of the uplift force, which is uplift force times 22 over 3. So overturning moment prime is equal to 11453.175 kilonewton meter. So that the new VARD X can be computed, and the new factors of safety can be calculated also. So factor of safety against sliding prime is mu Ry prime over Rx. Rx remains the same, mu s the same. So 0.45 of 2758.613 divided by Rx 1103.625. So factor of safety against sliding can now be computed. So it is 1.125. So factor of safety against sliding prime 1.125. Factor of safety against overturning is righting moment over overturning moment prime. So previous righting moment is 2482 over new 11453.175. So factor of safety against overturning prime is 1.788. Then For barred x prime, writing moment minus overturning moment prime over ry prime. So it is equal to 2482 minus 11453.175 over 2758.613. So barred x prime is now 3.273 meters, which is less than b over 3. So this is the worst case. Therefore, the soil pressure diagram is triangular maximum at the toe, then 3 times barred x, the length of contact. The soil pressure at the heel would be 0, as shown here. So if this is the base of the dam, this is the soil pressure diagram. Maximum at the toe, QT prime, then 0 at the heel, QH prime is 0. And the length of contact is 3 times barred x prime. So QH prime is 0 kilopascal. Then this is Ry prime. Ry prime is the volume of this pressure diagram, so that you will not forget. And this length is 3 times barred x prime. So Ry prime is equal to volume of soil pressure diagram 1/2 of 3 times barred x prime times Qt prime times 1 perpendicular to the board. Substitute 2758.613 is equal to 1/2 of 3 times 3.273 times Qt prime times 1. So from there, we can now compute the soil pressure at the toe prime, which is equal to 561.9 kilopascals. And that's it for this problem. Determine the thickness of steel plate rounded up to nearest millimeter every 2 meters from the bottom of a cylindrical tank, 3 meters in diameter and 8 meters wide. It is filled with molasses of specific gravity 1.5 to a depth of 6 meters, and the remaining 2 meters is under a pressure of 60 kilopascals. The allowable tensile stress in the steel is 60 megapascals. So for the solution, let's have the figure to serve as our guide in the analysis. So we have the tank, 3 meters in diameter, filled with molasses to a depth of 6 meters. This 2 meter space would be airspace, and it is subjected to 60 kilopascals pressure as shown. So for the formula for tensile stress, cylindrical tank, it is pressure diameter over 2T. That's the point at the bottom. And let's call the pressure there as P sub O. So tensile stress is pressure diameter over 2T. So thickness is pressure diameter over 2 times allowable tensile stress. So this is our working equation. For the pressure at the bottom, it is 60 plus specific weight of molasses 1.5 times 9.81 times 6, and we convert that to megapascals. So this is in kilopascals. Specific 60 plus specific weight of molasses times 6, so it is equal to 148.29 kilopascals or 0.14829 megapascals. Substitute in this formula here. So thickness at the bottom, required thickness of steel plate is pressure 0.1489829 megapascals, diameter in mm 3000 mm, divided by 2 times allowable stress, tensile stress 60 megapascals. So cancel megapascals, and TO is in mm. So solving for the required thickness at the bottom of the tank, thickness of steel plate 3.707 mm. So we round this up to 4 mm. So the thickness at the bottom, T sub O, is 4 mm. And let's indicate that's the thickness of plate at bottom. Then 2 meters up from the bottom, let's call the pressure there as P sub 2. So P sub 2 is 60 plus 1.59.81 times 4, because this is 4 meters. So 60 plus specific weight of molasses 1.5 times 9.81 times 4 meters. So P sub 2 is equal to 118.86 kilopascals or 0.11886 megapascal. Substitute in this formula here, 0.11886 times diameter 3000 mm over 2 times 60 megapascals. So T sub 2 is equal to 2.972 mm. So we round this up to 3 mm. So T sub 2, which is the thickness of the plate 2 meters above the bottom, is 3 mm. Then for the next 2 meters, this is 2 meters, so call this P sub 4, and that's 2 meters. So P sub 4 is 60 plus 1.5 times 9.81 times 2, because this is 2 meters. So P sub 4 is equal to 89.43 kilopascals, or 0.08943 megapascals. So substitute into the formula, T sub 4 is 0.08943 times 3000 mm over 2 times 60 megapascals. So T sub 4 is equal to 2.236 mm, and that is rounded up to 3 mm. So T sub 4 is equal to 3 mm, that's the thickness of plate 4 meters above the bottom of the tank. Then P sub 6, which is equal to P sub 8, because this is now the airspace subjected to 60 kilopascals. The pressure is 60 kilopascals, or 0.06 megapascals. So therefore P sub 6 is 60 kilopascals. That's also equal to P sub 8 here. So the thickness is the same for this portion of the tank for the last 2 meters. So T sub 6 equals 0.06 times 3000 over 2 times 60 megapascals. So it is equal to 1.5 mm and rounded up to 2 mm. Therefore, T sub 6, which is 2 mm, that's the thickness of plate 6 meters above the bottom of the tank. And T sub 8 is also 2 mm, that's the thickness of plate 8 meters above the bottom of the tank, or at the topmost level. So that's it for this problem. Problem 34. The triangular and rectangular sections are being considered for the design of a small freshwater concrete dam. From the standpoint of resistance to overturning, about C, which section will require less concrete and how much less in kilonewton per meter of dam length. Concrete has specific gravity of 2.4. So here's the figure. We have triangular section and rectangular section. So for the triangular section, we have horizontal force here, which is equal to the volume of pressure diagram, or from hydraulics point of view, specific weight of water, barred H area, where barred H is 7.5 over 2, and area is 1 by 7.5. So that's the location of the force, and it is 1/3 of 7.5 from the bottom, so 2.5 meters from the bottom. This is the weight of the dam section A, and this is 1/3 of A. So this distance from C, horizontal distance from C, is 2/3 of A. So that's the reaction at C as our guide, and this is 2/3 of A. So F is gamma water 9.81, barred 8 7.5 over 2, area 1 by 7.5, so 275.906 kilonewtons. Then weight A is specific weight of concrete 2.4 times 9.81, volume 1/2 of A times 7.5 times 1. Simplifying in terms of A, weight of dam section A is 88.29 A kilonewtons per 1 meter width perpendicular to the board or screen. Then summation moment about C equals 0, because that's the condition here. So 88.29 A clockwise moment times 2/3 of A, then equals F 279.906 times 2.5. Solving for A is equal to 3.4233 meters. Therefore, weight of section A can now be computed at 8.29 times 3.4233 meters. So weight of A in kilonewton per meter is 302.2 kilonewtons per meter with perpendicular to the screen. For B, so we have same F, 2.5 meters from the bottom, same magnitude also, same direction as this, and weight B, which is located B over 2 from C horizontally. That's the reaction, and this is B over 2. So weight B is equal to weight of this masonry, 2.4 times 9.81 times volume of this rectangular section, 1 meter to the board. So 2.4 times 9.81 times B times 7.5 times 1. So weight of B is equal to 176.58 B. Then summation moment about C equals 0. 176.58 B times B over 2 equals F 275.906 times 2.5. Solving for B, B is 2.7951 meter. So the weight of B can now be computed per meter. 176.58 times 2.7951. So weight of section B is 493.6 kilonewtons per meter. So this is higher than that of A. So the difference is 493.6 minus 302.2. So the difference is 191.4 kilonewtons per meter. So for the conclusion and for our answer, dam A requires 191.4 kilonewton per meter less concrete than dam B. So that's our answer. Dam A requires 191.4 kilonewtons per meter less concrete than dam B. So that's it. That's our answer for this problem.